Okay, friends, today we will talk about Chapter 7, Section 1, Electric Potential. Chapter 7 includes 4 sections. First one is electric potential, the second is capacitance, third one current and resistance, and the last one is electric power. Let's start with electric potential energy. Electric potential energy is the energy just with a charge due to its position in electric field. You know, till now you learned that potential energy is the energy of position. Yani a spring, if you compress or stretch a spring, you give energy to that spring, or spring gain energy. Or if you hold a book from ground or from table, then you give energy to that book. The book gain energy, potential energy, because of its position. Same as here, we will discuss potential energy in electric field or in an electric field. Electric potential energy is a component of mechanical energy. Till now we learned that mechanical energy includes kinetic energy, gravitational potential energy, elastic energy. Today we add electrical potential energy. So let's discuss how it happens. In order to understand electric potential energy well, let's talk about firstly gravitational potential energy. In gravity, we learned that every planet applies the object on it. So this force is called gravitational force. When you hold any object or throw any object, it comes back on ground because the earth apply a gravitational force on it. Here there is a ball and its height is h, and assume that we drop it. When the ball fall on the surface, what will happen? The change in the gravitational potential energy of the ball will be delta PE is equal to PE final minus PE initial. As you see here, when the ball falls on the surface, on the ground, its potential will be 0. At the top, it has a potential of mgh, and the result will be negative mgh. When the ball falls, at the top it has energy, and when it falls, it loses all of its energy. So we say the change in its energy is negative. And change of its potential energy is equal to negative mgh. Here we choose h. H is the distance. Since it's in vertical plane, we write h. It can be d also. Okay, change in potential energy is equal to negative mgh. Now we can discuss electrical potential energy. If you look this field, it is same as gravitational field. And just I choose to the right because gravitational force applies only downward, but electric force can apply in all direction. Here, electric field lines terminated to the right. I think you learn it. Electric field lines always start positive terminal. Here is positive, and it goes to negative terminal, negative charge. Or electric field lines start from positive charge and terminated to negative. So left side is positive, right side is negative. If we put a test charge here, Q, where will it move? Positive will push it and the negative will pull it. So with the result of these two forces, it will move to left. We say this electric field push it. So as gravitational force, there is an electrical force which is equal to Q multiply E. Electric field apply that force on a charge. So when the electric force push it, we say electric field does work on a positive charge here and in the direction of electric field lines. What this force depends on? The change in electric potential energy depends on the charge here. If we put a slight charge, then the energy will be less. If we put more charge, electric will be more or big. Electric field, it depends on electric field also. And it depends on distance, how many distance or displacement we can say, how many meters the charge is carried is important. So delta PE, electric potential energy, it is in joule. Q, charge of particle, its coulomb. E, electric field, and it is Newton per coulomb. D is the distance in the direction of field, it is meter. I want to share two notes with you. The first one is, here we study with positive charge, and we observe that when the positive charge moves to the right, its potential energy decreases as negative QED. Instead of positive, if we use a negative charge, then the negative and negative will be positive, so change will be positive. Yani if a negative charge, if we put here, I think all of you agree, it will move to the left. Because here is negative, the left side is positive, so if we put the negative charge here, it will go to left. It will move from lower energy to higher. So its energy will increases, so this part will be positive. And the second, if a charge is carried in direction perpendicular to the field, if we carry the charge in this way, since D in electric field doesn't change, pay attention, we move it perpendicular. So D will be 0 here, there will no change in potential energy. Yani if you put instead of D here 0, then potential energy change will be 0. Means that its potential will be constant. It is something like you hold a book and walk this book. The energy of book will not change. When you hold it, you give an energy to the book, but when you move with the book, book's potential energy does not change because its height does not change. Let's solve an example. As a particle moves 10 meters along an electric field of strength 75 Newton per coulomb, its electrical potential energy decreases by 4.8 10 to 16 negative 16 joule. What is the particle charge? Given potential energy for negative 4.8 because decreased. 10 to negative 16, electric field 75, D is 10. If you calculate it, our equation is delta PE is equal to negative QED. And if you put the values their places, Q will be, if you divide each side by ED, Q will be delta potential energy over ED. Then if you put values, Q will be 0.064 10 to negative 19. If you write it as significant form, 6.4 10 to negative 19 coulomb. So it is positive, means that it is a positive particle. It's a proton. Now let's talk about a few potential difference in electricity, or in these titles you will discuss it too much. In order to understand electric potential difference, firstly let's discuss electric potential. Electric symbol of electric potential is V. When you buy a battery, you will see on it that 1.5 volt, 6 volt, 3 volt. That volt represents its potential, yani its energy. Electric potential is the work that is needed to move a charge in an electric field. Yani you want to move a charge in an electric field, you have to give an energy to that charge. This energy given to that charge is called electric potential. We have written its equation as potential is equal to potential energy divided by charge. Yani potential energy needed to move a charge. We know that potential energy, units of potential energy joule, and unit of charge will be coulomb. So when you divide them, it's potential unit of electric potential will be volt. What does this mean? In order to move 1 coulomb charge under the electric potential 1 volt, we need 1 joule energy in order to move. Yani we have 1 coulomb charge, for example, and we want to move in an electric field which has a 1 volt potential. We need 1 joule energy. Potential difference. Potential difference, you know meaning of delta. It means the difference between 2 points. So if it says potential difference, means that delta V, the potential difference between 2 points. Electric potential energy that is needed to move a charged particle between 2 points. If you observe here, delta PE over Q, PE is QED we learned in previous title. So when you divide this, Q will cancel to each other. Let's pass on page. Delta V will be negative E multiply D. Yani in an uniform electric field, potential depends on the electric field and D. Let's see here, the potential difference depends on D. Okay, I want to explain here what is uniform electric field and what is non-uniform electric field. Here positive side, negative side, because electric field to the right. This is uniform electric field. Means that in every point of the field, electric field is constant. For example, if electric field is 5 Newton per coulomb, in every part of it, electric field will be same, constant, 5. Like it is like our G. G is 9.81 in every part. But potential energy of an object can change. After 1 meter, it will be different. After second meter, its potential will be different. If you hold it 20 meter, its potential will change. Same as here, the electric potential also will change in the field. It depends on D. When the D increase here, potential will increase, potential difference. Yani if it moves 1 meter here, it will be small. If you move 5 meters, then you instead of D, you will put 5. So potential difference will be 5 times more. I will explain it with a picture now. Now this is non-uniform. As you see here, when the light rays move away, they separate, move away to each other. Yani in closer part of the charge, electric field denser. And when they move away, it is smaller or less than this part. So it is non-uniform here. Okay, let's discuss electric potential on a picture here, on a figure. There are 2 plates and its positive terminal is 1, negative terminal is 0 volt. Means that when any electron or any particle move from plus terminal, it has 1 volt. When it moves the other side, it will lose its potential and it becomes 0 volt. There are 4 levels here, A, B, C, D. If any particle move from A to B, yani when we write here delta VAB, means that potential energy between A to B. It moves A to B. What does delta means? Final minus initial. So if I write for AB, VAB, delta VAB will be VB minus VA. Because particles move A to B, final minus initial. Let's solve an example. What is VAB? It says, so VB is potential at B 0.5 volt minus potential at A 0.75. So the result is 0.25. Means that if a particle move A to B, let's see here, A to B, it lose 0.25 volt. So it is negative. Another potential difference between CA now. It moves C to A. Look at here, C to A. Or look at this part, C to A. Means that it is equal to VA final minus VC initial. And the result is positive 0.5. if a particle move here from C to A, initially 0.25, finally 0.75, it gains energy. So its energy will be positive, potential. So 0.5 volt will be delta V. Electric potential produced by a point charge. We learn in a field. Now let's discuss electric potential produced by a charge. We know that when two charges approach to each other, they will pull or push to each other. Means that every charged body produces a field around itself. So a particle produces an electric potential around itself also. Here there is a charge, and this charge will produce potential around it. But at point A, what will be its potential? When calculate VA, it is equal to KQ over R. KC, Coulomb constant. What will happen? Gentlemen, this is potential. But when we discuss potential difference for a point charge, in physics we accept that infinity is accepted as the ground level of a point charge. Yani, when the potential of the point charge will be zero at infinity, because R will be infinity here. When you divide it, it will be zero. So in order to calculate potential difference at any point, means that we bring charge particle from infinity to that point. So infinity initial, this point is final. When we calculate delta potential here, delta potential will be potential at A, negative potential infinity. So the result will be potential difference for a point charge will be KQ over R, same as potential here. But as I say, the logic is a few different. For point charge, we calculate just electric potential at a point, and when we talk about potential difference, we assume that this charge particle brings from infinity to that point. Let's understand it with a simple image. Now, instead of infinity, assume that this point charge, test charge is brought from A to B. So what is the potential difference AB? Means a particle, charge particle, moved from A to B, or potential at A and potential at B compared here. VAB is equal to potential of B, because it moves B final, minus potential of A. So potential difference between 2 points we can calculate by using this. In book there is no such example, but at least the definition of them we should give and explain. Most questions related with fields. Here there is another subtitle, let's say, the superposition principle. Sometimes the charge can be closer to each other, and then we can ask what is the electric potential at a point. Here Q1 will produce a potential there, Q2 will produce a potential, and Q3 will produce a potential there. So at point O there will be a superposition, and we can calculate total potential by adding them. Let's solve one more question. A charge moves a distance of 2 centimeter in the direction of uniform electric field, which is 215 Newton per coulomb. As the charge moves, its electric potential energy decreases by 6.9 10 to 19 coulomb. Find the charge on the moving particle. What is the potential difference between two locations? There are two questions here. These are given. And let's see question. Firstly, charge wanted. So charge is equal to delta potential energy over ED. If you put the values there places, at the end charge will be 1.6 10 to 19 coulomb. And then the potential difference wanted. In order to calculate, we need electric field and D. Delta V is equal to E multiply D. And when you calculate it, put their values to their places, you will see that potential difference is negative 4.3. A battery. Let's talk about battery. The last subject of this section is battery. Batteries are devices energy stored devices that provides constant potential difference between two locations. Yani in the batteries, I think you have seen a broken battery. There are some chemical mixture. The battery separate negative and positive particle. It accumulate negative particle one side and positive particles to other side. And when we connect them, the negative charge flow through the positive terminal and they give off light. So, thanks.